Please welcome Brian Lauer.
Thank you so much. And this theory, I mean, this is it. It's the theory. It's all-encompassing. And it answers a lot of questions. But if you don't know what the questions are, the answers aren't going to mean anything. So we're going to fly through these questions. Put your pens down. You won't be able to keep up. Just sit back and just trying to comprehend what's happening here. So question, how do marine fossils get over 5 miles high, you know, in the Mount Everest, above sea level? You know, and what causes a mountain to rise? And that's what I love about this theory. He comes at it from an engineering perspective. And what's the mechanism? What's the force? What's the energy to raise a mountain? And what formed the Mariana Trench, 36,000 feet deep in the Pacific? I mean, that's deeper than Mount Everest is high. And why are the trenches mainly in the Pacific Ocean? And why is the Pacific so much different than the other oceans? It's got 40,000 seamounts. These are volcanoes a kilometer high off the bottom. Why aren't they everywhere else? What caused this mid-oceanic ridge? A 46,000 mile mountain range going around the whole Earth at the bottom of the ocean. What caused that? And why are the mountain ranges parallel to this ridge, the mid-Atlantic ridge? Why is that? And how did the 90 East Ridge form? It's a 3,000 mile crack in the Earth that points directly to the Himalayas. How does something straight like that form? How does a mountain range form? By stretching it in two directions. And you can see these are vertical cracks, horizontal and vertical. They're straight. That means they're tension cracks. Those rocks were getting pushed apart, and then they cracked, and then the pressure released. Most mountains come together by compression, and they rise up. And we'll talk about that a little bit later. And why are there plateaus next to most of the mountain ranges? And it's what mechanism would force, you know, a large volume of low-standing continents to rise rapidly a mile in the air? And it's a double-sided mystery because the Colorado Plateau seems to grow downward and upward at the same time. How does that happen? What about the inland seas? What forms them? And where did the sediment come from? You know, that averages a mile deep on the continents. And how come if it doesn't have carbon in it, and like limestone, it's 65 parts granite and 35 parts basalt? Why does it have that ratio? And how did it get cemented together? You know, you can have sand out there, but that's not turning into sandstone unless it's mixed together with something like calcium carbonate and quartz. How did it get so evenly mixed? And how do you get continental layers? You know, anybody ever been to the Grand Canyon? Okay, those layers don't just stop there. Those go everywhere. They're continent-wide. How do you lay down something like that? And the evolutionists say, you know, the present is the key to the past. Present processes explain everything in the past. And Randy Galuza says, if I was in college now, I'd be asking them, what present process lays down continental layers of sediment? What present process is making fossils all over the world? You know, something was different in the past. And then Tim Clary, this is the Zuni mega sequence. That thing goes all the way around the world. These layers are worldwide layers of sediment, not just continent-wide. They're worldwide. How does that happen? And how do canyons form under the ocean? You got submarine canyons at the end of most of the major rivers, like the Congo and the Ganges. And then how does a little Colorado river cut a canyon 18 miles wide? I mean, that's probably the next town over. How does a little river cut a canyon that wide? And where did all the limestone come from? Because when limestone forms, it releases some carbon dioxide. And there's 60,000 times more limestone in the earth than carbon dioxide in the atmosphere. And Walt Brown, he would meet every week with Bob Dietz. He's the guy that coined the term seafloor spreading. And he asked him one time, hey, where'd all the limestone come from? And Bob says, beats the blank out of me. Yeah. They couldn't explain it. And then the Grand Canyon. What caused the side canyons? Just as deep as Grand Canyon, but there's no river. Those box canyons. What about barb canyons flowing the wrong way? And then that big funnel. Once you see that funnel, you can't unsee it. And where'd all the dirt go? The guy used to give tours there, and he'd say, yeah, I dug that. And the little kid asked him, where'd you put the dirt? And that question haunted him the rest of his life. It's like, where did the dirt go? There's 800 cubic miles of dirt from the Grand Canyon that are missing. And that's nothing because they had to scrape off 2,000 cubic miles above it before they could start cutting the canyon. Where'd all that dirt go? How did mesas, buttes, and spires form? You know, how about petrified trees? How did that happen? And how did the lineaments form? Now, lineaments are straight line features on Earth, like a fault, straight. And that's kind of like, what were we talking about that was straight? Those tension cracks are straight. So we're going to talk about that. How does a canyon form under 2 kilometers of ice in Greenland? How do you get lakes with liquid water under 2 miles of ice in Antarctica? Especially when it's below freezing in the summer there. How does that happen? And how does the South Pole says it's mostly covered by ice, but fossils show there are crocodiles, dinosaurs, and palm trees once lived there. You know, if it was warmer, yeah, maybe the dinosaur and the crocodile could live there if it was warmer, but how are you going to get a palm tree to grow where it's dark for 4 months of the year? That doesn't make sense. And then on the other side of the world, you got snakes and tortoises and alligators and shrews and stuff growing in permafrost. And that doesn't make sense. And the mammoths. Who's heard about the frozen mammoths? Okay, yeah, they're frozen in permafrost. And there was one of them that was really special. What was special about that one? He was frozen standing up. Do things stand up when they die? No, this thing was buried alive, flash frozen. It still had identifiable food in its stomach. How are you going to flash freeze an elephant? It has to be like 150 degrees below zero to flash freeze them. And how did it get so cold so fast? And then how come they never thawed out? Very, very interesting questions. And what caused the Ice Age? Evolutionists have 40 theories, which means none of them work. And the neat thing is, I saw this. It's hard to find a picture of the glacier. And when I saw it, I was jumping up and down. My wife can attest to that. But look it up there in Alaska. What's missing in Alaska during the Ice Age? Do you see that? Ice. It's permafrost up there. They didn't have ice in the Ice Age. Same thing in the Siberia. They had permafrost. My son went to Pensacola Christian College, and his roommate was from Inuvik, Northwest Territory, Canada. So he's above the Arctic Circle, where there's permafrost. I said, well, how do you do your pipes? I mean, we put our pipes in the ground so they don't freeze. Your ground is frozen. How do you do that? And he said, we have utilidors, where they're above the ground. You either drive under them or drive over them, but they're heated so that they don't freeze. And then it's dark, and then it's light, and that's where he is now. He was in Florida. And how do redwoods grow in the permafrost north of the Arctic Circle? And these things are huge, 90-some feet. And then they got special isotopes in them. They have a different ratio of oxygen, which brings us to deuterium. Deuterium, hydrogen is a proton and electron. Deuterium is the proton, electron, and a neutron. And how come the comets have twice as much deuterium as the oceans? If all the oceans came from comets, they should have the same amount of deuterium, but they don't. And this is a physics question. How do you fuse past iron? This is one of the greatest unanswered questions in physics, according to the U.S. National Research Council. How do you fuse past iron? And that was back in 2000. And this guy says, we're made of star stuff. The problem is, we aren't sure exactly how the stars did it. And then why do comets have stuff from Earth? They're supposed to come from the Oort cloud, way far, 50,000 astronomical units out there, An astronomical unit is from here to the sun. So 50,000 times farther than the sun, that's where the comets come from, and so they should have all this other stuff. But yet we find stuff in them that's water, salt, silicates, limestone, cubonate, olivine, organics, bacteria, all that stuff that's on Earth. And they're going to say that life, that the comets brought life to Earth. And you're going to see why that's backwards later on. And cubonate only forms in the presence of scalding hot water. How did comets contain materials only made in scalding hot water? There's no scalding hot water out there. I mean, much less liquid water. I mean, we're the Goldilocks zone. We're the place with water. And then how does an asteroid get a moon? It's really hard to get a moon, because if they're coming together, they might just speed up and zoop and go on the other way, or they might smash and break each other apart, And they can't explain how Earth got its moon. They got 4 theories now, which means none of them work. And so there's some unanswered questions. And then you get these peanut-shaped comets and asteroids. How do you get that? They came together very gently, and this really bothers them. It says, it's a major mystery how 2 objects, each to the size of skyscrapers, could collide without blowing each other to smithereens. This is especially puzzling in a region of the solar system where gravitational forces would normally involve collisions of up to 4,500 miles an hour. Anybody ever play pool? Do those balls stick together or they bounce off? That's what should have happened here, but it didn't, and it really bothers them. It calls them a major mystery. And how do chondrules form in meteorites? Meteorites are like melted rock or something. Electric charge was in there. They think it got hit by lightning. Well, how are you going to get lightning in outer space? And why is the near side of the moon so much pounded much than the far side? The near side and the far side are totally opposites. The near side has been pounded, a lot more earthquakes, lava flows, and the far side is just peppered. And how does that happen? It looks like the near side got shot with buckshot, which is very counterintuitive because the Earth protects the near side, just the Earth itself, and then you throw in the gravitational force of it. It'd be very hard to hit the near side, and yet that's where most of the damage is. And you'd think it would be the outer side. And then how do you get erosion on Mars from water? These erosion canyons from water. And then the comets, if they came in from the asteroids, that Oort cloud, it should be a 50-50 mix. They should all be going back, there shouldn't be a dominant direction that they're going, but 90%, 93% of the short-term comets, which is less than 100 years, they're all going the same direction as the Earth, prograde. And then the mid-period ones from 100 to 700 years, it's 70-30. And then when you get the long-term ones over 700 years, then it's closer to a 50-50. But if they all came in from the Oort cloud, it should be 50-50 all the way through. So there's a problem with that theory. And so this is my question. Why doesn't the moon orbit the equator? You ever thought about that? Most satellites, if not all satellites in the solar system, they go around the equator. Except for all the planets, we don't go around the sun's equator. We're off a little bit, which is hard on their theory. But if the moon went around the Earth's equator, we'd hardly ever get a perfect solar eclipse. But it's not. It's on the same plane as what the Earth is going around the sun. So I don't know. I don't know if this theory answers that or not, but I just throw it out there. So we've gone through a lot of questions. And if there was a theory that could answer all those questions in a coherent manner, wouldn't that theory be worthy of study? Right? Yeah, I think it would be worthy of great study. And the question at the end is, well, why isn't it? And we're going to show you how to figure that one out. Okay, so now prepare to color in the details. Again, this is my favorite talk. I love talking about Walt Brown. People call him today's Isaac Newton. He's just brilliant. And my goal is to get him the credit he deserves.